Welcome to Data Center Dialogues, the podcast where we explore the innovations shaping the future of digital infrastructure. I'm your host, Alison Matte, and today we're diving into a topic that's heating up, literally, direct liquid cooling. With AI workloads growing fast and sustainability targets in sharper focus, data centers are under pressure to rethink how they cool. Joining me are two experts who live and breathe this stuff, Wendy Torell and Maria Torres Arango from Schneider Electric. We'll unpack our recent white paper, 10 practical ways to harness energy and water efficiencies with direct liquid cooling, and why this matters for your bottom line and the planet. Welcome, Wendy and Maria. Wendy, let's start at a high level. Liquid cooling isn't brand new, but it's clearly getting a lot more attention right now. What's changed in data centers that's pushing people to take it seriously?
Alison, that's an important distinction. Liquid cooling isn't new, but the need for it has definitely changed. And what's driving this need is server power density. GPU-based servers, as we all know, are drawing far more power and generating far more heat than traditional CPU-based systems. And once you start getting into densities above what air cooling can handle efficiently, you have to rethink how the heat is removed. Direct liquid cooling does that by circulating a coolant through cold plates that sit directly on the hottest components, the GPUs, and the heat is then carried away by the coolant, rather than trying to move it with massive volumes of air. That shift creates real opportunities to improve energy efficiency and in many cases, water efficiency too, especially when you step back and you look at the entire cooling facility from the chip all the way to the outdoor heat rejection.
Maria, Wendy touched on how this shift opens up energy and water efficiency opportunities, but the impact isn't the same everywhere. How should operators think about those trade-offs when they're trying to align cooling design with sustainability goals?
Direct liquid cooling allows you to balance electricity and water use, which has the potential to reduce your sustainability impact. Key here is to understand your sustainability priorities and operational constraints. For example, if your data center is in a water-constrained region, your priority is most likely to eliminate the use of water in the cooling process. Likewise, in a location where electricity has a higher carbon intensity and water is plentiful, energy reduction will take precedence over water use. Understanding opportunities to minimize water and energy use is important because this translates into lower greenhouse gas emissions.
So let's get practical. Your white paper outlines 10 ways to improve the energy and water use with liquid cooling, 7 design factors, and 3 operational choices. Let's break those down, starting with a couple of the design factors. Wendy, the paper mentions the impact of coolant temperatures as a big driver. Can you explain why this is?
Sure. First, it's important to understand that IT vendors specify the operating temperature range allowed for their liquid cooled servers, and staying below the specified maximum is generally necessary for proper IT performance and to maintain the warranty. But within their specified range, operating at a higher coolant temperature improves energy efficiency because it allows for more free cooling hours and reduced chiller load. In our analysis in the paper, we show that increasing temperatures from 25 to 45 C reduce the energy use by roughly 30 to 40%. And for adiabatic systems that rely on water consumption, this same temperature increase can also cut the water use by 40 to 60%.
Maria, the paper also mentions different types of cooling distribution units, or CDUs. How does the CDU choice impact energy use?
That's an important question. There are 2 fundamental types of CDUs, liquid to liquid and liquid to air. Liquid to liquid CDUs are more energy efficient than liquid to air CDUs. This is because liquid to liquid CDUs transfer the heat directly to the facility's chilled water system. Liquid to air CDUs instead transfer the heat to the air into the IT room, and this heat needs to be transferred to the facility cooling system through coolers. So it adds an extra step in the heat removal process.
That makes sense. So why would someone use a liquid to air CDU?
Liquid to air CDUs are useful in situations where you don't have a chilled water system, for example, in a retrofit scenario, or in situations where you only have a handful of liquid cooled racks.
Okay. So when you mentioned retrofit, that makes me think of design. So Wendy, any other design drivers that are important to highlight for impact on sustainability?
Yeah, sure. First, heat rejection architecture. Air cooled chillers with economizers are typically more sustainable than water cooled chillers with cooling towers, especially in regions where there's water constraint. Second, dedicated heat rejection systems matter. When liquid cooled loads share a chiller plant with air cooled loads, think about this, it limits how efficiently the liquid cooled side can operate because of the temperature it's allowed to operate at. And then third, I'd say component selection, prioritizing components with high efficiency, a long life expectancy, and material compatibility helps reduce energy consumption and embodied carbon associated with manufacturing, spare parts, system replacements. So it's helpful to look for vendors that are transparent with this type of information. And they'll generally include it in their environmental product disclosure documents. So that can be really helpful in making informed comparisons.
Okay. So let's shift to operations. Maria, what's often underestimated once a system is live?
Thank you for asking that question. It's controls and visibility, which are probably the most underestimated pieces. Liquid cooling introduces new variables, things like flow rate, pressure, and fluid quality. Operators may not be used to tracking these in detail and understanding how they play a role. Without good monitoring and integration with systems like DSIM or the building management systems, you're essentially flying blind. Monitoring and controlling capabilities give operators real-time view of how the system is performing, not just how it was designed to work. You can see how changes in workload of your data center affect the temperatures, the flow, energy use, and you can identify inefficiencies or early warning signs before they turn into problems. Um, this visibility is what allows teams to eventually move from fixed conservative operating points, like those Wendy mentioned at the beginning with the temperature, to optimized parameters, and eventually to dynamic control, adjusting pump speeds, temperatures, and cooling capacity based on real demand. This is how you improve efficiency without increasing risk. And it's also how you maintain performance as IT requirements evolve.
You mentioned maintain, right? Maintenance doesn't always get a lot of airtime in these conversations, but it can make or break long term performance. When it comes to direct liquid cooling, what actually changes for operators day to day? And where do you see teams getting caught off guard?
That's a great question, Allison. Maintenance really does matter more than some people expect. With liquid cooling, you're introducing a lot of new components, pumps, filters, you've got fluid chemistry to contend with. And if those aren't managed well, the system slowly gets less efficient and, more importantly, increases the downtime risk. Coolant quality is a big one. If the fluid chemistry drifts or contaminants start to build up, the flow is going to start to be restricted and pumps are going to have to start working harder. That means more energy. The same goes for filtration. Clogged filters is going to increase your pressure drop. And again, it's going to mean higher energy use. So, bottom line is poor maintenance isn't just a reliability risk. Over time, it's quietly driving up that energy consumption and it can even shorten the life of the equipment. So, the good news is that with the right type of monitoring and routines in place, it is very manageable and it'll pay off both in performance and in sustainability.
Okay, we've talked a lot about today's system. Let's look ahead for a moment. Maria, what future trends stood out to you while working on this paper?
Yeah, so better heat reuse, more intelligent controls, and eventually the possibility of fully liquid cooled servers with minimal air.
And I'd also add that we're also watching developments in different types of coolants and two-phase direct liquid cooling systems, though single-phase direct-to-chip still is very effective and practical today.
Okay. Any closing thoughts before we wrap up?
I would say big takeaway is that liquid cooling, first and foremost, is about obviously supporting this higher density that we're seeing today, but it also can help data centers meet their sustainability goals if it's done thoughtfully.
I'd add that there is no single right design, and the how sustainable your design is, it comes really from understanding the trade-offs between energy, water, risk, and then making intentional choices based on what matters to you.
Wendy, Maria, thank you for the insights. For our listeners, the full white paper is linked in the show notes. That's a wrap on this episode of Data Center Dialogues, powered by Schneider Electric. I'm Alison Matte. Thanks for tuning in. If this was valuable, subscribe, rate the show, and share it with someone on your team. See you next time as we dig further into the future of energy tech.
The content of this podcast is for informational purposes only, should not be undertaken as financial, economic, legal, business, tax, or investment advice. The information, statements, views, and opinions should not be construed as the provision of advice by Schneider Electric or as an offer to buy or sell any products or services or to make or consider any investment or course of action.